Okay, so let's unpack this. The continuous pressure to compress high fidelity audio and do it in real time is just one of the biggest challenges out
It
there.
really is.
We know streaming dominates. I mean, Cisco reported audio and video was something like 82% of all internet traffic, and that was back in 2021.
Right. And while traditional codecs like Opus and EVS are, amazing pieces of engineering, they just hit a wall.
A hard wall, especially at those ultra low bite rates. If you're dealing with anything more complex than speech, like music, the quality just falls off a cliff.
And that cliff, that performance ceiling from traditional DSP, is exactly what this paper is targeting. So for our deep dive today, we're getting into encodec, a state-of-the-art neural audio codec.
Hmm.
Our mission here is to give you, our expert listeners, a real breakdown of the architecture, the training, basically how it uses this quantized latent space to get high-fidelity compression in real time.
Yeah, this isn't just a results review. We want to really dissect the ML engineering here. We're going straight into the nuts and bolts, the end-to-end architecture, that clever residual vector quantization scheme.
RVQ, yeah.
And two things that really stood out to me. A really simplified spectrogram-only discriminator and this novel loss balancer. That thing is genius.
It's a very complete paper. It really positions this as a production-ready solution. And you can see how every decision, from the layers to the loss functions, fits together to make the whole pipeline work.
Okay, so let's start at the foundation, the encodec architecture itself. The core design seems to be all about simplicity and streamability.
It is. At a high level, it's a very standard setup. You have an encoder, which we'll call an AXIP, quantization layer, a decoder, and decoder dollars. A simple, streaming, convolutional design.
And inside that encoder?
The structure is pretty deliberate. It kicks off with a 1D convolution, then goes through 4 convolution blocks.
And those blocks are a usual unit plus a strided convolution, right, for the downsampling.
Exactly. And then, and this is a key part, it feeds into a 2-layer LSTM. That's for sequence modeling, before you get to the final 1D convolution.
Okay, the LSTM is interesting. You know, in a field that's obsessed with speed for real time, LSTMs can sometimes be a bottleneck. Was that trade-off worth it?
The paper argues yes, absolutely, for perceptual quality. The LSTM just gives you better sequence modeling over that latent space, which you really need for, say, complex music.
Right, makes sense.
And the ablation studies seem to back it up. The quality gain was worth a tiny computational hit, especially since the rest of the pipeline is so streamlined and convolutional.
And to get that latent space small, the downsampling has to be pretty aggressive. For 24 kilohertz audio, the strides are 2, 4, 5, and 8.
Correct. And that aggressive downsampling means the encoder is only spitting out a latent vector 75 times per second.
Just 75 times. And the decoder just mirrors that with transposed convolutions to build the signal back up.
Precisely.
Okay, so let's talk about that streamable design. The padding is critical for getting that ultra-low latency they report, right?
It is. This is one of those key engineering details. A non-streamable model might just use equal padding, before and after the time step.
The standard way.
Right. But for the optimized streamable setup, they shift all the padding to happen before the first time step. By preloading the buffer that way, you minimize the processing delay.
And that's how they get to output the first 320 audio samples, which is about 13 milliseconds, as soon as the first 320 input samples come in.
Exactly. That 13.3 millisecond latency figure is all about that optimization.
And they had to make another change for streaming, didn't they? Something about normalization.
They did. A subtle but really important one. They swapped out layer normalization for weight normalization.
Why?
Well, layer norm needs to compute statistics across the time dimension. In a streaming setup where you're just getting small chunks, that becomes unstable. Weight norm doesn't have that dependency, so it's the right choice for stability here.
Okay, that makes sense. So moving from the architecture to really the heart of the compression, that quantization layer, this is where residual vector quantization, or RVQ, comes in.
RVQ is the engine here. It's what takes the continuous floating point output from the encoder, called Ziller, and turns it into a set of discrete indices that you can actually compress.
And it does this iteratively.
Yes. Instead of quantizing the whole vector at once, it quantizes the input, then it calculates the leftover error, the residual.
And it quantizes the error.
And it quantizes the error. You keep doing that step by step, accumulating codes for more and more fidelity.
What are the codebook specs they're using?
Up to 32 codebooks, though it's 16 for the 48 kilohertz models. and each codebook has 124 entries.
So 10 bits per codebook. The final byte rate is just how many of those you decide to use.
Exactly.
Now, training a system like this with discrete codebooks, you always have the problem of gradients. How do you backpropagate through a non-differentiable step? And how do you update the codebooks?
Right. So for the codebooks, they're updated with an exponential moving average, an EMA, with a decay of 0.99. It keeps things stable. And if a codebook entry isn't getting used, it gets replaced by a sample from the current batch.
To avoid codebook collapse.
Yep. And for the gradient problem, they use the classic straight-through estimator. For the backward pass, you basically just pretend the quantization step was an identity function.
The STE gets the gradients back, but you still need to tell the encoder to produce outputs that are, close to the codebook entries. That's the commitment loss.
That's the anchor loss, yes. It's an MSE loss between the input of the quantizer, 70, and its output, STQ8. The key detail is that the gradient is only computed with respect to the input. This loss, summed across all the residual steps, pulls the encoder's output towards that discrete manifold defined by the codebooks.
But the real genius of using RVQ here is the built-in multi-bandwidth support. You don't need a different model for every single byte rate.
That is the big operational win. A single train model can hit multiple targets 1.5, 3, 6, 12 kilobps just by using a different number of codebooks.
How does that work in training?
During training, they just randomly select a number of codebooks to use, say a multiple of 4. So the model learns to pack the most important information into the first few codebooks and then add finer details with the later ones.
That's incredibly elegant. Okay, let's switch gears to the objective function, which is where some of the deepest innovation is. The overall generator loss, LGV, is a sum of a few things.
Right. You've got your reconstruction losses, the adversarial loss, and that RVQ commitment loss we just talked about.
Let's start with reconstruction.
So you have a simple L1 distance in the time domain, that's L $. But the real workhorse for Fidelity is the frequency domain loss.
And that's not just one loss.
No, it's very comprehensive. It's a mix of L1 and L2 losses over Mel spectrogram, but, and this is the important part, it's calculated using 7 different time scales, from 205 all the way up to 2 an hour.
So using all those scales means the network can't cheat. It has to get the details right at every level, from quick transients to long, slow, harmonic shifts.
Exactly. Now, for the perceptual part, the adversarial loss, they use just one discriminator network, the multi-scale STFT discriminator, or MSSTFTD.
Which is a simplification, right? A lot of models stack multiple types of discriminators.
They do. But they found this was enough and very efficient. The MSSTFTD is made of identical networks, but they operate on multi-scaled, complex-valued STFTs.
Complex-valued, so not just the magnitude.
Correct. The real and imaginary parts are concatenated. It gives the discriminator much richer information. And they use 5 different SPFT window lengths to make sure it's scale invariant and less prone to mode collapse.
And for the training itself, it's a hinge loss for the discriminator and a feature matching loss for the generator, but they also had a trick to keep the JANs stable.
They did. They throttled the discriminator updates. It only gets updated with a probability of 23 at 24 kilohertz and half the time at 48 kilohertz. But the real leap in stabilization engineering is the loss balancer.
This is the highlight for me. I mean, anyone who's spent days just tweaking lambdas for a complex loss function will appreciate this. Can you walk us through how it works?
The basic problem in any multi-loss objective is that the gradient norms can be wildly different. The gradient from your L1 loss might be, orders of magnitude bigger than the gradient from your feature matching loss.
So your hyperparameters end up just fighting the numerical scale instead of actually reflecting how important you think each loss is.
Precisely. The loss balancer fixes this. It redefines the weight, lambda, to be the actual fraction of the total gradient that comes from loss dollar.
And it does that by normalizing.
It does that by normalizing. It takes the gradient of each loss and divides it by the exponential moving average of its gradient norm.
So you're decoupling the hyperparameter from the native scale of a loss. You just set lambda based on its conceptual importance, and the balancer handles the scaling under the hood.
It's a beautiful piece of engineering. It simplifies tuning massively, and according to the paper, adds a ton of training stability, especially when the adversarial and reconstruction losses are really fighting each other.
Okay, let's get to the payoff then. With all this clever architecture and training, did it actually deliver state-of-the-art results?
It absolutely did. They used subjective MUSHRA tests, with human listeners, which is the gold standard.
Yeah.
And ENCODEC hit SOTA scores across the board.
What's the headline comparison?
The big one is this. ENCODEC at 3 kilobps sounds better, on average, than Lyra V2 at 6 kilobps, and even better than Opus at 12 kilobps.
Wow. So you're talking about maintaining quality at a quarter of the byte rate of a traditional high performer like
The
Opus.
efficiency gain is huge. And
Right.
then they push it even further with optional entropy coding.
Right. This is a post-quantization step. It uses a small transformer, I believe.
It does. A 5-layer, 8-head transformer. It's trained to be a language model over the quantized codebook indices.
So it's looking for statistical patterns in the codes to compress them even more.
Exactly. It predicts the next code index based on the previous ones. The transformer creates a probability distribution, which then feeds into a range-based arithmetic coder. This can squeeze the bandwidth down by another 25 to 40%.
So that 3 kilobpps model could get as low as 1.9 kilobps.
Potentially, yeah.
But there has to be a trade-off. That kind of predictive modeling adds latency, doesn't it?
It does. It's a small hit to the initial latency, because to decode the current frame, you need to have already received part of the next frame's indices, so you can't just flush the stream frame by frame anymore.
Okay, so let's talk pure real-time performance. What's the real-time factor on a single CPU?
The numbers are impressive. On a 2019 MacBook Pro, the 24 kHz streaming model at 6 kilobps hits an RTF of 9.8 for encoding and 10.4 for decoding.
So almost 10 times faster than real-time.
Right. Even with things like the LSTM, the engineering is so tight that it just flies.
And what about with the heavier entropy coding step included?
Even then, it's still faster than real time. It drops to an RTF of about 1.6 for both encoding and decoding, so it's still very, very efficient.
Finally, the big one for music lovers. Stereo results at 48 kilohertz. This is where low bitrate codecs usually die.
And the results are just astounding. Encodec at 6 kilobps doesn't just beat Opus at 6 kilobps, it's perceptually comparable to an MP3 running at 64 kilobps.
64 kilobps. That's a compression ratio of 256 to 1 for similar subjective quality.
It is. It really shows that these neural approaches excel at modeling the kind of complex stereophonic information you find in music, even under extreme constraints.
So to sum up, we've taken a deep dive into encodec. We've covered its robust convolutional LSTM design, the incredible flexibility from the residual vector quantization, and the power of that streamlined MSSTFT discriminator. And I think for practitioners, that really elegant loss balancer.
I think the work is clear evidence that neural codecs have just moved past the limitations of traditional DSP at these low byte rates. You can get high-quality audio on connections that were previously, unusable for anything but muffled speech. And that loss balancer technique is something people can take and use in GAN development anywhere.
It really does raise an important question for the future, though. Given how much encodec relies on subjective MUSHRA tests to prove its quality, and it clearly wins there, how do our objective metrics, things like VSQL and SISNR, need to evolve? They need to somehow learn to correlate better with the very complex nonlinear distortion that these neural models create. The success of encodec almost feels like it's pointing out a fundamental flaw in how we currently measure audio quality automatically.